With every approximation, there's a certain amount of error involved, and we have two upper bounds for the error. So effectively, the worst case scenario for what the error could be. Let's consider this example where we are attempting to approximate the integral of f of x, which is 2x to the 7th, over the interval 1 to 2. And I want to find worst case scenarios for the error using trapezoid rule and the worst case scenario for the error using Simpson rule. So the error on the trapezoid rule is at most a constant m, which we'll discuss here in a minute, times b minus a, that's the interval that you're integrating over, cubed, divided by 12n squared, where n is the number of rectangles you're using in your domain. It's your partition size. So let's talk about this m. That's the only thing here that's not well defined. This m is an upper bound for the magnitude of your second derivative. So you need to find a second derivative of your function and maximize it over this interval a to b. So let's do that now. If our function is 2x to the 7th, then our first derivative will be 14x to the 6th. And our second derivative will be 84x to the 5th. So you could go back to calculus 1 techniques, and in order to maximize this second derivative, you would have to differentiate it. So find a third derivative, set it equal to 0, test your boundary points, or you can just understand the geometry of the function. This second derivative over the interval 1 to 2 is monotonically increasing, which means that its maximum occurs over here at the right-hand endpoint of the interval 2. So this second derivative over this interval is bounded above by its value at 2, right? The maximum of the second derivative is right there. So my second derivative at the value of 2 is 2,688. So that can be used as our m value over here. An upper bound of our second derivative on our interval is 2,688. Now, b minus a, we are integrating over the interval 1 to 2, which we will cube. And we have 12, a constant down there in our denominator, and n, our number of rectangles that we're using, or in this case, the number of trapezoids that we're using. And it specifies in the problem that we should use 8. Okay, running through the algebra here, we get 3.5. So the trapezoid approximation might have an error less than 3.5, but worst case scenario, it's going to be 3.5. Let's do the same thing and find an upper bound for the error associated in Simpson's rule. Here it has the same format, a constant m times b minus a, this time raised to the 5th. And we divide by not 12, but 180, and not n squared, but into the 4th. So this m is not an upper bound on your second derivative. This is actually an upper bound on your fourth derivative. So we need to find our fourth derivative and figure out how large it can be over the interval 1 to 2. So our third derivative is 420 x to the 4th. Our fourth derivative is then 1,680 x cubed. So again, you could find another derivative, a fifth derivative, set it equal to 0. Use your typical calculus 1 optimization techniques on this fourth derivative in order to maximize it, or just look at the geometry. If we look at the interval 1 to 2, this fourth derivative right here is monotonically increasing. Therefore, for all of the same reasons as above, its maximum occurs at 2. So our fourth derivative has a maximum value of its value at 2, which is 13,440. So this can be used as our m value. This is an upper bound on the fourth derivative over this interval. So we have 13,440 times b minus a, the interval is still 1 to 2, which we will raise to the fifth, and divide by 180, and n, if I still want to use a partition size of 8, I have 8 to the fourth. Oops, 8 to the fourth. All right, running through the algebra here, we find an upper bound for the error on a Simpson's rule approximation of 0.0182. So that's not the actual error in the Simpson's rule approximation, it's the worst case scenario. It's the upper bound on what the error can be. So a good question would be, if I want a certain amount of error, how many rectangles in my domain, what size of partition should I have in order to have that certain amount of error, right? Because we know that if we increase the number of rectangles that we use, we get a better and better approximation. So this question states, how many subintervals should we have to ensure a Simpson's rule error less than 10 to the minus 6? So our Simpson's rule error, let's write the upper bound again. M b minus a to the fifth over 180 n to the fourth. And we want this error to be at most 10 to the minus 6. So our m is, again, because it's Simpson's rule, an upper bound on the fourth derivative. That was 13,440 for this specific function. b minus a was 2 minus 1 to the fifth. We have the 180, but this time the n is unknown. That's what we're trying to figure out. How many subintervals should we use? And I want this to be at most 0.1234 10. So 10 to the minus 6. So you can flip everything upside down and write this as 180 n to the fourth divided by 13,440 times the 2 minus 1 is just a 1, so 1 to the fifth is a 1. And now make sure to flip the sign. This will be greater than or equal to 1 with 6 zeros, 1, 2, 3, 1, 2, 3. And you can solve this for n by throwing the 13,440 over to the other side, divided by 180, and taking a fourth root. So n will be at least 1 million divided by 180 times the 13,440, and then a fourth root of this, which after running through the algebra, you get 92.9. Oops. So you obviously can have 0.9 of a partition, so n has to be at least 93. So if you use at least 93 subintervals, you'll have that small of an error.